Hello ladies and gentlemen, and welcome back to GGS 300. This week we have the 5th laboratory session, and we're going to basically be picking up a lot of those concepts and techniques that we covered within the lecture, focusing on data sampling, but we're going to actually be carrying out some calculations, just using some very basic R code in order to kind of work out how this is basically carried out in practice, okay? So I'm going to start with calculating confidence intervals, which you should remember from the lecture slides already. So I'm just going to go back to where we were within the actual lecture so you can kind of refresh, look at the equations that we're going to apply here. Hopefully you've understood the different terms that we need to understand in order to use this set of techniques. And essentially what I want to do is focus first on how we actually generate these confidence intervals, okay? So remember we've got this sample mean here, which lies in the middle of this normal distribution. And then basically we have an upper limit and a lower limit for where we think we can be a certain a level of confident in order to kind of estimate where we think the population parameter is. So for example here this diagram is basically being 90% confident that the mean lies somewhere within this shaded area, okay, for the population based on the sampling that's been carried out. So what does that mean in practice? Well, essentially what we're going to need in order to actually to calculate this equation here is we're going to need the x bar, which is the mean value. So here it will be the sample mean. We need a z value, so this is going to be the number of standard deviations, for example, above the mean that represents this upper limit here. And then we're going to need the standard error, which is the population standard deviation divided by the square root of the number of samples, okay? So we're going to add all of those different pieces of information which we have into the R memory. So we've got the mean value of 5, we've got the standard deviation of 2, and we've got 50 samples, okay? Let's imagine then that we want to be 95% confident that the mean exists within a set range, okay? In which case we're going to need to find the z value for this point here, but for 95% confidence range. And the way that we're going to do that is we're going to use the Q norm function, okay? So you can look for help if you need to with the Q norm function. So here we go, we have the normal distribution here, so you're basically providing it with a quantile, so you're providing it with a value between 0 and 1, which indicates the quantile that you want to find for the number of standard deviations above the mean in this instance, okay? So here we're focusing on finding the number of standard deviations that contain 45% of the data, 47.5% of the data above the mean, okay? And the reason why that is obviously is before we focused here on this being 90%, and then there would be 5% in the lower limit and 5% in the upper limit. But obviously if we're focusing on being 95% certain, then we're going to have a 95% width here, and that would leave 2.5% for the upper limit and the lower limit here. So we're going to basically get that upper limit value, which is going to be at the, it's going to have 97.5% of the values within that distribution below it, okay? So we can basically give that value to Q norm, and it's going to give us the number of standard deviations above the mean that that point is at within our distribution, which is 1.95. And then we need to multiply it by the actual standard error of the mean, okay? And that we know how to do because we already have this equation here. It's the standard deviation divided by the square root of the number of samples, okay? So that's going to get us our standard error value, and I'm going to enter it here into the memory, and basically that's 0.554, and I'm not going to list all of the other decimal places for that particular value, but this is basically how you find it. And then once you do that, we can then start to estimate where the lower bounds are, okay? So I think the important thing is if you're still stuck on Q norm, I've written some notes here for you to basically follow through. So just remember that R has that built-in table that estimates the p-value for the entire curve, and is able to estimate it starting from the left. and that's the point at which 97.5% of the values fall below in this instance. Okay, so you can look more at either the previous lectures, or you can look more at ztable.com for why we're using that particular value. Okay, but remember, it relates to the probability of where certain values lie across that whole distribution in a standardized way. So look, now we've got that value which represents the standard error based on that z value. We're then able to essentially just do the final part of this. So obviously we've calculated this right-hand part here, the z and the standard error, but we haven't either subtracted it or added it to the actual mean in order to find these upper and lower limit points. Okay, so here we're going to find the lower bound for the confidence interval. We're going to subtract the SEZ value from x bar, and that's going to produce us with a value of 4.44. And then we can do the same for the right, which produces a value of 5.55. Okay, so essentially what we've got is we know that we had a mean of 5, but then we know that we're able to kind of estimate at the 95% confidence level this confidence range for where we think the population mean is going to be, and that ranges from 4.446 up to 5.554. Okay, so this has been relatively abstract, but don't worry, we will be able to work through some more examples in the book, but also today. So look, that's when we're using the normal distribution. So you remember that the normal distribution you can use when you have a large enough sample size. So let's say the sample size is over 30, and that's easy for you to basically produce those estimates. The difference, of course, comes when you then start to have a smaller sample size, and then you may need to use a different distribution, for example, the t distribution, and that's going to require maybe some different calculations in order to produce that confidence interval. Okay, so let's use pretty much the same values. So we're using 5 for the mean, and we're using 2 for the standard deviation, but we're only going to have a sample of 20 data points, okay? And when we actually place that into the memory, that's going to mean that we need to use a different distribution quantile function here, okay? So before we use Q-norm, sorry, here we're going to use QT for the student t distribution. And the difference here when we use QT is that we're going to provide it with the percentile value that we want. So you can see down here it lists the argument for the function. We're going to provide it with the percentile value that we want to provide it with. So it's a value between 0 and 1, which represents the point at which a certain percentage of the values fall either above or below that point. But we're also going to need to provide it with the number of degrees of freedom, okay? So what we have here is basically the same calculation. We're just using this different function. So we're saying, give me the point within the t distribution at which 97.5% of the values fall below it, okay? And we have the number of degrees of freedom here that we're going to provide, and obviously it's a small sample. We're not going to have all of those extreme values, so we're going to use n-1 to represent the fact that we don't have all of those extremes. And therefore that's going to produce a value of 2.093024, which we can then multiply by the standardized error, okay? So we can get that standardized error and place it into the global memory. It's 0.936 here. And then we can get those left and right confidence interval points around the mean basically by subtracting this standard error from the mean value. So that's going to get the lower one, 4.06. And then also when we get to the x bar, we're going to be able to add the standard error, so it's 5.93, okay? So we get those different confidence interval value ranges of 3.06 and 5.93 here. So that's how you calculate it if you've got a much smaller sample and you need to use the student t distribution, for example. Okay, so you're going to remember that also within the lecture we covered some aspects of sample size calculation. So this is basically maybe where you want to kind of rearrange the equation that we've used to calculate the confidence intervals, but this time you want to estimate exactly how many samples you need to collect in order to be certain to a certain confidence level that you are within a certain range of a desired value. Okay, so remember that I gave the agricultural example, and we basically went over the calculations for a farmer. And that farmer basically wants to know what the mean yield of corn is per acre to a certain confidence level. So let's say they want to be 95% confident that their estimate is correct, and 95% is a fairly standardized confidence level. You'll be familiar with that if you've carried out any statistics before. And then essentially we're going to have a preliminary sample in order to collect things such as the population standard deviation. Of 50 acres. Okay, so we're going to go out and we're going to do 50 acres of surveying to find the mean corn yield, and then essentially we're going to get a mean of 74 bushels per acre of corn with a standard deviation of 16.65. Okay, when we've got that information, we can then start to investigate this question: how many acres do you need to sample to be within 3 bushels of the true mean? Okay. So look, we know what the actual mean value is going to be. Sorry, not the mean value, the standard deviation value, the sigma value here, S, which is 16.65. Let me just clear this environment so that you can actually see this clearly without other things getting in the way. Okay, so we've got this 16.65 bushels value for the S, for the standard deviation. We're saying that we want to be within 3 bushels of the true value, so we're going to enter that as the E. You'll remember that we rearranged this equation so that we could get the sample size on the left-hand side, and that means that we basically need to multiply the Z value by the sigma to get the numerator, divide it by the E value, the error value, and then take the square of that. Okay, so what we're going to do now is we're going to get that Z value. We want to be 95% certain, so that means that we're going to again have that 5% spread between both the bottom and the top parts of the distribution, which means you're going to have 2.5% at the top, 2.5% at the bottom, which means we're going to therefore, when we want to find the upper bound value, you're going to have 0.975 to find that upper point. So that means 97.5% of the values fall below that standardized value that we obtain for 1.95. And then we can multiply this by the standard deviation and the error and square it in order to get the value of interest, which is 118.3265 acres that need to be surveyed in order to be within 3 bushels of the true mean, okay, for estimating the mean yield of corn per acre. Okay. So, of course, we've already sampled 50, so we can't. So we're going to have to basically subtract those from the number that we obtain here, because we don't want to waste time going out and surveying more than we really need to. Okay, because we're always going to be fairly frugal with our time when we're carrying out research. You don't get that much additional benefit from surveying beyond that point. You want to find the most accurate, kind of least cost value for us to basically get the value that we're interested in at the particular confidence interval, okay, the particular precision level that we find acceptable. So look, we then want to subtract those 50 from there, and we end up getting 68.3265, and therefore we're going to round that up so that basically we're going to need to survey another 69 acres. Okay. So they're kind of the quite high-level examples that I gave within the lecture, but they give you a bit of context for how we use this. Now let's actually pull in some data and do some work with some real data, because the large majority of times that you guys are going to be working with real-world problems, you're probably going to have your own data. You're probably going to want to pull your own data in and actually use that to essentially do some data manipulation and find some answers to some real-world problems. So we're going to be sampling from a distribution here, and essentially what we're going to need to do is first download the data set that I've placed on Blackboard. Obviously by now I hope you've also managed to download all of the lab code that I've got here. I'm assuming you have. And then essentially what you need to do is you need to actually import this. So here we're going to use the read.table function, and we're going to basically say that this is a file path, this folder path, and we're going to give it the file name lc.txt. Okay, so just remember that this one-liner that I've given you just basically says, go into the folder where this code is and give me the directory name, and that's how you basically get this single line here. And it's obviously much better than me giving you a fixed folder directory structure, because that string is going to be different whether it's on your machine or my machine. Okay, so this is a really nice way for you to basically get that folder and be able to share it with lots of other people, which you will do at some point. So look, this just basically, this file.path function produces the file path, so it's basically taken that previous path and added on the actual file name lc.txt. Here is a good example. And then we're able to read in everything that comes from that particular file. Okay, and we're going to allocate it to an object in our memory called LC. Okay, and it has all of these different variable names. You can even look at it. This is actually an extraction of data land categories. So imagine this is 1 kilometer squared areas, and then they have a land category. It's the land classification that's been basically converted into a numerical indicator. So these are integers, so just imagine them as categorical indicators for agricultural land or forest or ocean or whatever. Then we're able to go into our height text file. So they're both text files, obviously. And what we're doing here is, again, reading in that same data. It's just going to find the different file name height, and it's going to place it into the memory here. And then we're able to combine that into a single data frame. Okay, so we're going to basically say, go into my LC file. We're going to refer to a column. Column is always referred to by the $ here. And then we're also going to do the same for the height data set. We're just going to get the V1 column. And this is basically going to provide us with a single set of data for this one column, for the land classification, and for the height of each one of those kind of 1 by 1 kilometers squared tiles that we have land classification for. Okay, so just imagine this is basically an exert that also has its digital elevation model associated with the land classification, and that means that we can put them both into our new data set called new, as you'll see up here. Okay, so we've got each one of those columns. So this is the land category type, 21, agricultural, 41, ocean, etc. And then for height, here we've got this, and I'm assuming this is in meters. Okay. So look, now we can get the population mean height for this set of data, and it's 11.68905. Okay, so we know that that's the population mean, but I just want to show you that we could take the sample mean here, and you can see as I press Control Enter, we're getting a sample, and we're getting the mean from that sample, and we're just getting 5 heights each time. Okay, so and it's going 11.2 meters, 13.9 meters, 12.2 meters, 11.6 meters. Obviously, it's taking a random sample at each opportunity as I run that through the R engine. Now we're able to basically take a random sample of 50 and calculate the 95% confidence interval. Okay, so this is similar to what we've done before. We're going to use that sample function again. We're going to say take 50 samples of the height, and we allocate it to this variable name sh. So here we go, we've got that vector in the memory now. We're able to do the same to get the x bar. What we're going to do is take the mean for that sh sample that we have, sample of height sh, and that's placed into the memory. And then we can do the same for the standard deviation and the length. Okay. And then finally what we're going to do is we're going to get that standard error value, so that we're going to say we want to be 95% confident. We obviously therefore have 5% as the significance value, and because we're focusing on a normal distribution here, we're going to need to split that 5% between the lower and the upper half. So 5% divided by 2 is going to be 2.5, which means we'll have 2.5% at the top part of the distribution, and 2.5% at the bottom part of the distribution, which lies outside of that particular confidence interval that we've set. Okay. So look, I can get the standard error here once we've got that z value from Q norm, which is 1.95, and then multiply it by the standard deviation divided by the square root of the number of samples. And the standard error is 1.838. We then subtract that standard error from the mean to get that lower bound. So obviously the mean is going to be 11.4, the lower bound is 9.5, and then we can get the upper bound, which is going to be 13.2. Okay, great. So let's plot that on an actual graph so that you can see that. So now we've got the histogram of those data samples here. We've got those heights, some going quite high up to about 40 meters above sea level, some here with the modal value is around here between 5 and 10. And we can add this, line which represents the mean value here, which is, I think it was 11.4. We can then add the lower level line for our bottom confidence interval, which is going to be at 9.56, and we can add the upper boundary line, okay, which is going to be in blue also at 13.24, and you can see those values just here. So this is our mean in red, and then we have our 95% confidence interval representing the point at which we're 95% certain the population mean lies within that range based on our sample, okay? So let's also create a distribution of sample means and make a histogram. So what I'm going to do now is basically create an empty vector called SAM for sample. So this is a vector, it's empty, and we're going to go and use a loop again, okay? So I covered loops in previous sessions. So just remember that for a loop, what we're saying is for I in sequence 1 to 50. So it's just saying that each time we loop through a sequence of 1 to 50, I is going to take the value of 1 in the first instance, and then it's going to take on the second loop the value of 2, and then on the third loop it's going to take the value of 3, and then each time it's going to iterate through, and basically where you place this I, in this case we're going to say index the value to that row in this vector SAM, okay? So basically we're going to say is we're going to take the mean from a sample of 5 data points of heights, and we're going to allocate it the column row in the sample vector, which is currently empty. So the first time you loop through, we're going to the first column row, so the first row of SAM, and the second time you loop through, it's going to go into the second row of SAM, and so on and so forth until you loop through, okay? So look, let me loop through now and produce a histogram based on a sample of only 5. So this is quite a small sample, and therefore this doesn't look really that kind of normally distributed as we would expect. So I just want you to play with this loop basically. So you can increase this so that you basically end up with a sample size of 100 being taken each time, and that looks a lot more normally distributed. And you can also change the actual number of loops that you're going to take, okay? So I want you to basically go through this function and play with these two values, okay? So you see here, I've stated that you can change the loop number, which is going to be here, from 50 to 100 to 1000 to 10,000, and also play with the sample sizes, okay? So you can do it for 10, 30, or 50. So let's have a go here where we use 100 and we use 10, and we generate our distribution, and now we can start to see, as we've both increased the sample size and we've increased the number of loops, we're starting to get something that looks a lot more like a normally distributed data set, okay? So we can even add 1,000 loops, and that now we're getting even closer. You can even add 10,000 loops. Again, you're getting a much closer kind of normally distributed shape, okay? So I think you should play around with this. You should also change some of the sample sizes. Obviously, you're going to get an even nicer normal distributed curve as you start to increase those values. And that's going to be really important because it demonstrates those kind of... It's quite similar to how we demonstrated that this conforms to the central limit theorem, which I'm about to do shortly. So I'm going to give you a bit more on that in a short period of time. Okay, so finally I'm just going to finish off by giving you a little bit of information about stratified samples. Okay, so in the previous examples we were just using the sample function, which just randomly picks values for the certain number that we've estimated and provides those values to us, okay? And they're called, it's basically uniform sampling. It means that every value has an equal probability of being selected relative to every other. What we want to do here, for example, is actually play with a stratified sample. So let's say that we have a different number of categories and we want to pull samples from within those categories in order to basically get a sample which is broadly representative of the overall population. So we've got most of this information already, and what we're going to do is we're just going to go into our new data frame, which we've got here. We've got the land category column here, and I'm just going to basically sort all of those values. Okay, so these are categories of land types, land classifications, and essentially what we're doing here is we've sorted them from smallest to largest. So you can see a lot of them are 21, 22, 23, and then we've got a small number of 41 and 43. So let's say that we're only interested in the values that are 22 and 43. So imagine that these are agricultural land and forest, and we basically want to take samples of height from these two different strata. Imagine that we're going to basically need to kind of reflect the fact that there's different numbers of land classifications within our sample that we actually have. Okay. So what we're going to do first is get the size and the mean for each of these populations. So we know that we can access the new data set, and we can access this land classification column by using the $sign, and we can basically say, okay, so give me as a logical indicator all of the outcomes from that data frame that we've got, which equal the land use 22. So you can see it returns as true or false. And then within R's logic, what we can do is we can say, okay, for all of those that are true, which are basically those equal to 22 here, we can then just get the heights for those. Okay, so this little function just allows us to go in and get just the heights for those land categories that are equal to 22. And that's basically saying if it's a true value rather than a false, return the associated height value that's in the height column. So that's how we get this set of data here. So basically for the length, we're going to get 55 values equal to 22. We're going to get a mean height of 10.83. And then let's do the same here for 43, where we're going to get only 6 values, and we're going to get a mean height of 32.25. Okay. So let's say that we want to produce a proportional sample. So let's say that we want 20 samples. If we've got 55 plus 6, it's 61, and therefore broadly, it's a bit of an approximation, we're going to have about 10 to 11% of those values being from this second group of the land classification 43. Okay. So that's about, it represents about 10% of the overall number of the sample that we produce, which relies just on those two different land classifications, 22 and 43. So what we're going to do is we're going to basically say, okay, so if we're going to take 20 samples and we're going to basically want 10% from the 43 land classification, that will mean that we will need 2 values, and that will mean that we need 18 values from the other classification, which is basically 22. So basically we need to use the sample function, and we're going to go and get all of those that are equal to 22 and get the heights for them, and we're going to sample just 18 values. Okay. So when we do that, what we end up with, I'm going to run this here, is we're going to end up with this set of 18 values, and the length of the strat here just demonstrates that we've got 18. And then basically just to finish off, what we're going to do is we're going to append to our strat, so our stratified sample vector, a new set of values, and this new set of values are basically going to be those land classifications equal to 43. And we're going to get all of the heights for those equal to 43, and then we're going to just sample 2 of those values, okay, and then we're going to append them to this strat value. So when we do that, we end up with basically the first 18 values here coming from our first land classification type, which is 22. And then we have our second set of values here coming from our second land classification number, which is 43. Okay, and we get a sample overall of 20 different samples. So that basically provides you a bit of an overview as to how you might actually stratify the sample so that you've got something that's proportional to your kind of overall desired composition based on how you design your research study. So look, I'm just going to finish now with one last little demonstration where we're going to basically go through a little example on the central limit theorem. Okay, so I know we kind of touched on it on one of the previous examples as we were iterating through and changing those parameter values in the loop as for how many samples we have and how many times we're iterating over that loop and the kind of shape of the distribution. But here I can provide you with a nice little example which just kind of demonstrates those properties that we're interested in for this really important theory which kind of underpins a lot of the modern statistical techniques that we use. So remember, there's principles associated with the central limit theorem. So even if your population is not normal, if you have a sufficiently large sample, say over 30, then the distribution of your sample means will be normal. This essentially means that we can assume normality when we are using inference to assess the mean. Okay. And we're going to use an inbuilt data set called rivers, which you're able to have a look at. So I've just emphasized it here by looking in the help menu at the README for the different data sets. This one is for the rivers data set. So this is the lengths of all major North American rivers. There's 141 major rivers provided by the USGS, and I think that these are all in miles. So let's have a look at the plot for the distribution of those rivers. So you can see here most rivers are under 1,000 miles, and then we have this long tail of rivers that really stretch out to be quite long. So I assume this is the Mississippi River over here, which is almost 4,000 miles, and then the rest down here are far more frequent and also far smaller. So we can get the mean for this distribution here, which is 591 miles, the median, which is 425, and the standard deviation, which is 493. Okay, so it's quite a large standard deviation. And I think the important thing to notice is that we know this isn't normally distributed because you don't have the mean and the median basically being pretty much exactly the same value. You have a mean that's much higher and a mean that's much lower, which indicates that it's basically positively skewed and that you've got a lot of positive values which are basically dragging that mean value up. So we can even look at that by testing the skewness, and obviously with a skewness above 1, this is quite significantly skewed. And obviously this is a positive number, so it's positively skewed out to the right of your screen over here. So let's take a sample of 5 rivers and calculate the sample mean and repeat it. Okay, so if I get a mean sample here for 5 river lengths, you can see that this is iterating quite a lot. So we had 519 as the first estimate of the average, 818 as the second, 623. So this is quite a large amount of variation that's occurring, particularly given that the true population mean is about 591. Now we're able to basically iterate through a loop of say 1,000 samples and see what happens. So let's create a vector here called sample 5, and let's say we're going to iterate through 10,000 times, and each time it's going to place that sample mean where we've taken 5 samples into this vector of interest, and then we're going to plot it. So when we do that, we still have quite a skewed distribution, so it's really not looking like it's normally distributed here, and it's because we haven't sampled a large enough number of data points. Okay, so if we basically repeat this whole process, but this time we take sample 10, so this is where we're going to take 10 rivers at random from this data set, and we're going to sample them and take the mean value, and then we're going to do that 10,000 times and place it into our memory. We're going to end up with something that looks a little bit like this. So we're starting to become closer to a normal distribution. I think also I kind of skipped pretty quickly the fact that we had a mean value here of 592, and then we had a median of 538. And that means that there's still quite a significant distance between these two. Whereas here, when we increase the sample size, this distance starts to decrease. And relative to the first one, where we were still highly skewed, so above 1, the skewness here has dropped below 1, which is an indicator that we're starting to get closer to a normal distribution. Okay, then let me just finally finish this off by saying that we're going to take 100 samples here for each mean that we're going to take, and we're going to take 10,000 means, okay, because we're going to iterate through this loop 10,000 times. Take a mean each time from a sample of 100 points. And when we do that, we end up with something that's much closer to a normal distribution. So we know that the mean of the population is 591 miles. And we can see that here we're actually getting the center of the distribution pretty much directly on top of that value. And I think what's also important is not only do we have the mean converging there, but also the median value is pretty much very close to this too. And we can also see that the skewness has pretty much now gone to pretty much close to 0. Okay, so there's a little bit of movement in a negative direction due to random variation. But essentially we started to produce a distribution that we've sampled from our population data set, which is normally distributed, as we proved here. So Gaussian in shape, and it very much looks like a bell shape. Okay, remember when we talk about the bell-shaped curve, that's the normal distribution that we're interested in. Okay, great. I don't want to take any more of your time. I've covered all of the materials that I want. So I just want to say thanks for tuning in. There's going to be the new assignment, which is going to be set based on this. And don't hesitate to reach out to me if you have any questions about the work that's been set. But hopefully by the time you go through the book, you've looked at the lecture, and also you've looked at the laboratory sessions here, you'll be able to kind of fit the pieces of the puzzle together, the jigsaw, and work out how to kind of address those questions which are within the assignment. Okay, well, thanks very much for tuning in. It's been great to see you again, and I look forward to seeing you all again soon. Thank you. Goodbye.